please.
Okay, thank you, Katja, for inviting me to give this talk. So I'm going to discuss the following question. So it's within scattering by an inhomogeneity of bounded support. And the question is, given an inhomogeneous media, so the refractive index with a particular modality, whatever the acoustic, electromagnetic. So given a scattering media, does it exist an incident wave that if you probe that inhomogeneity with that incident wave at a particular frequency, then there is no scattered field back? Okay, so the inhomogeneity, it's invisible with respect to that interrogating incident wave. So here is just a visualization, is a scattering by a ball with a constant refractive index and the incident field. And it's a superposition of plane waves that are called Hegel's function, you will see later. And if you send such a wave, very particularly chosen at a particular frequencies, then actually there is a field only inside, the scattered field is zero outside the inhomogeneity. So for those who are sort of new in this area, I like to cite this review paper that is written in sort of more broader sort of discussion at the notices that just appeared in this October issue, where we discuss all these things that I'm going to mention here. Okay, so let me just take one particular scattering model. Say I'm going to describe the scattering problem in R3, acoustic waves, but one can do it in R2, also RD, doesn't matter. Now, if there are other sort of models that describe the wave propagation in that particular media, the results that I'm describing today are not yet generalized. So I'm going to probably say that the results or part of the results I'm going to discuss today refer to this particular model, which is the media has bounded support. Then the support of the media here is denoted by D. What is required is that well, not necessarily, no assumption, but just the inhomogeneity has a refractive index n, and outside, for simplicity, the media is homogeneous with a scaled refractive index 1, and so the support of n-1 is exactly the scattering media. So in general, the boundary, I'm going to assume that the boundary is Lipschitz. And the incident field is a solution to Helmholtz equation in the entire R3. One could take point sources, but that's not the point. So let me stick with incident fields, entire solutions to Helmholtz equation. And in that case, the total field satisfies the Helmholtz equation with refractive index n of x. One could also consider, and everything I'm going to say can be generalized like verbatim generalization, if one has like potential k square u plus a potential of bounded support. But here is in the context of scattering by an inhomogeneity. Of course, the scattered field satisfy the outgoing radiation condition. Okay, so this is the model. And the important here is that actually the refractive index is in the lower terms, right? So if there is refractive index, like a conductivity type refractive index, some of the results that I'm going to mention here are not proven yet. Okay, so now, in fact, what is important when one discusses imaging inverse problems, so it's typically the measurements operator, which is is given in terms of the far field measurements or near field measurements, but anyhow, to understand the scattering phenomena by this inhomogeneity, one considered the scattering operator. So if incoming to outgoing operator that in the book by Melrose, it's called relative scattering operator. In Colton-Kress, it's a far field operator. Then in that case, well, actually there is, I think I'm missing a slide. Sorry, that's very weird. Anyway, this slide actually was supposed to be after. Okay, so I apologize. So actually, let me first introduce. No, there is a slide missing, and it doesn't matter. Anyway, so if I have the far field, this relative scattering operator that takes the L2 density to the far field pattern of the scattered field, and the scattered field, so basically in the model that I showed here, if you subtract the incident field from the total field, then one can write the equation in terms of the scattered field, and in that case it becomes an equation in R3 where the right-hand side is like a source term that involves the contrast n-1 and the incident field. Okay, so the far field operator, or the relative scattering operator, is related to the far field pattern, and the far field pattern is the asymptotic of the scattered, is the angular dependence of the, in the first term of the asymptotic of the scattered field as r goes to infinity, which makes sense thanks to Sommerfeld radiation condition, the outgoing radiation condition. Anyhow, so this is a far field pattern corresponding to a special incident field that is called the Helmholtz function, which is a superposition of the plane waves. Okay, so so this is basically the far field operator. So if the incident field is any solution to the Helmholtz equation, and that is the slides that I actually somehow is deleted by mistake, then the scattered field is going to satisfy this type of equation, where instead of Vg, which is Helmholtz function, one has the incident field. Okay, so now if I consider a general incident field, as I mentioned in the first slide, so the non-scattering question becomes, is it given the inhomogeneity ND, and can one construct an incident field UI, which is a solution again of the Helmholtz equation in the entire R3, and with wave number k, such that the scattered field satisfies this equation in R3, but is identically zero outside the support of inhomogeneity. So in other words, if the source term on the right-hand side is of this form, with UI being a solution to the Helmholtz equation in the entire R3, then can we find a compactly supported solution to this source problem, which is zero outside D. Okay, so in particular, if you have that far field or a relative scattering operator, then the question actually becomes now, can one construct a Helmholtz function? So is it possible to superimpose the incident, the plane waves, which is like this, it's exactly the superposition of plane waves, in such a way that that non-scattering configuration happens for this Helmholtz function. So this can be rephrased as, okay, at a non-scattering configuration, the relative scattering operator is not injective, and its range is not dense. Okay, and one sort of guess that this property that the far field operator is injective and the range is dense in the measurement space, it's an important property in order to solve the inverse scattering, because it has to do with whether the incident field brings back any information about the inhomogeneity. Okay, so in terms of the far field or relative scattering operator, this question has applicability in solving in reconstruction methods for solving inverse scattering. Okay, so now as one sees, this non-scattering configuration is given a sort of in terms of this set of equation, which is like an overdetermining problem, right? So you have the source that satisfy a particular equation in the entire R3, and the solution has compact support. So the natural question that arises is that, does this make sense at all? Is it possible actually that such non-scattering configuration exists? So anytime that you would like to answer such type of questions, so the first inclination is to sort of take a particular case for which you can get explicit solutions. And in this context, the explicit particular case is scattering by a ball with a spherically symmetric refractive index, okay? And so if actually one send this particular incident wave, which here is in R3 configuration, which is this is spherical Bessel function of order L, and YL is one of the spherical harmonics, can be any of the spherical harmonics, then one can compute explicitly the solution, the scattered field due to this incident Herlot's incident wave. And there is a coefficient here that is given in terms of the refractive index, the wave number, and the Bessel function, spherical harmonics, as well as solutions to the ODE, which is a radial part, the equation for radial part inside the inhomogeneity. So actually this expression for the scattered field give precisely the existence of two sets of interesting sort of wave numbers. So if the nominator here is 0, it means that the scattered field outside, because this is an expression of the scattered field outside the ball, is identically 0. And in this case, one is at the non-scattering configuration. So if there are zeros for which this determinant here, which is an entire function of the wave number, then there are non-scattering wave numbers. And just for a remark, the zeros for which the denominator become, so the zeros of denominator actually are the scattering poles that corresponds to this ball, right? So, but what I'm interested in is actually the zeros of the nominator, and it can be shown that in fact there are infinitely many real k for which this function here becomes 0. Okay, so I mentioned real k because if I talk about non-scattering wave numbers in this physical setting are real numbers, right? Because this function may also have complex zeros, and I'll connect with a larger set of wave numbers that are transmission eigenvalues. But it can be shown that in fact there is a sequence for given incident field of this form. There are infinitely many wave numbers that accumulate, real wave numbers that accumulate to plus infinity, for which this ball with refractive index n of r become invisible to this particular interrogating incident field, which, by the way, again, it's a Herlot's function with a particular density. So these results can be found in Colton Kress' book. In the fourth edition, there is an extended discussion on spherically symmetric media. There are also some examples that we have obtained for less regular refractive index, for which the contrast can oscillate up to the boundaries for which there exist infinitely many non-scattering wave number in this preprint. Anyway, to conclude, this is that yes, for the spherically symmetric configuration, one can find infinitely many wave numbers for a specially chosen incident field. Okay, and there are infinitely many incident waves. Okay. Which have non-scattering wave number that make the inhomogeneity invisible to these incident waves, because you can actually change L, the order of so there are plenty of incident field of this form. So you get a lot of incident field for which the ball is non-scattering with respect to that particular interrogation. So now, anytime actually before, when I was talking about this non-scattering and then connect to the transmission eigenvalue, I always got the question that is this spherically symmetric configuration stable? So now actually the recent results have shed light into it, but the direct connected work to this question is this paper by Michael Fogelius and Gini. They show that in R2, and if n is constant, then if you perturb the ball to an ellipse, then actually one can prove that maybe at most finitely many incident waves for which a Helmholtz function is non-scattering. So it's not a stable perturbation. So the configuration with respect to Helmholtz interrogation becomes unstable. But the main goal of this talk is actually to understand what happens in the general case. Okay, so since I know for balls there are such non-scattering wave numbers and a lot of them, what is the situation in the general case? So it suffices actually to study the problem, not the entire space, but if one takes a domain that circumscribes the inhomogeneity, say omega, then the non-scattering configuration becomes, so the wave number k, it's a non-scattering wave number, if one can find functions v and u such that the v solves the, it's in the place of incident field, solves the Helmholtz equation in the larger domain omega. U solves this source problem. Remember that the source it's supported so in D, because 1 minus n is supported in D. But U is required to be 0 outside of this inhomogeneity. So this problem is exactly what I described earlier, because if the incident field is a solution to the Helmholtz equation in the entire R3, then U is extended, it's 0 in the entire space. Okay. So when this question, as I try to explain, comes from a very simple physical question, non-scattering, and this was sort of open for a long time. And in effort to solve, to give an answer to this question, people broaden sort of relaxed the requirement for non-scattering configuration, and then see what happens. Basically try to find a necessary condition for which k is non-scattering frequency. So if instead of actually requiring that the solution of the Helmholtz equation happens in a larger domain, So one simply assumes that the part V satisfies the Helmholtz equation only in D, okay? And then the scattered field, this is in place of the scattered field, satisfy this equation with the source problem in D, and the fact that U is 0 outside D equivalently can be expressed to finding a solution to the source problem in H2D with the Cauchy data 0 on the boundary. Because if the Cauchy data are 0, and then if the scattered field satisfies the Helmholtz equation, then can be extended by 0 outside. Okay, so this is exactly the transmission eigenvalue problem. So if K, it's a wave, a non-scattering wave number, then of course K is a wave number for which this problem has non-trivial solution. So the K, the wave number, is a transmission eigenvalue. Now, the other way around is actually the big question that I would like to address. So it's not sufficient condition. So it's only necessary condition for K to be a non-scattering wave number. It's necessary that K is a real transmission eigenvalue. So if K is a real transmission eigenvalue, as you will see, it's not the K is not necessarily a non-scattering frequency. Okay, but this problem, which has less conditions, this is more overdetermined, is well studied, and a lot of research has happened. Basically, it's a different writing of this, as it's more familiar to people, of the transmission eigenvalue problem written this way, as two equations that share the same Cauchy data, because you write it in terms of the incident field and the total field, as opposed to the incident field and the scattered field. Anyhow, so but what it interests me in regard to transmission eigenvalues is that are there real transmission eigenvalues? Because if I want to find non-scattering frequencies, okay, at least I want to know that there is a set where I can look for such a non-scattering frequencies, and those, as I said, are real transmission eigenvalues. So this is a self-adjoint eigenvalue problem, so maybe complex eigenvalues also. So at least there are cases for which people know that there exist infinitely many real transmission eigenvalues. In particular, if the contrast it's in L infinity and doesn't change, so n it's in L infinity and the contrast doesn't change sign. So this is a good thing. So there is a larger set of wave numbers where I can look for non-scattering frequencies. Okay, so. But what I'm interested in, let me go back here, is actually if there is a K for which this problem has a non-trivial solution, does it happen that the V part, the eigenfunction V part, actually is a solution to the Helmholtz equation in a larger set than D? Okay, that's basically what comes down. Okay, so this question has been open for a very long time compared to the first studies of transmission eigenvalues. And the first icebreaker was this paper by Blast and Paivarinta and Sylvester in 2013, which basically showed that in some particular straight corners, that if the support of inhomogeneity contains singularities of like corner type singularities or edge type singularities in R3, roughly, and assuming that the refractive index at the corner point is not equal to 1, so the contrast is not 0, then any incident field is scattered by this inhomogeneity. Okay, a lot of work follows the first paper by Blast and Paivarinta and Sylvester, so I'll get to it next. But what is important in this result that I stated here, maybe not in the most kind of rigorous assumptions, but roughly any corner singularity scatters any incident wave. So the point here is that there is no restriction on the incident field. So as long as the boundary has a corner singularity and the refractive index is not 1 at that corner, then any incident field scatters. And this is very nice because this enables to prove a uniqueness result for inhomogeneities that are convex polyhedron with convex polyhedron support from the measurements due to one single incident plane wave. Okay, has to be convex because when you consider two inhomogeneities, and then you would like to make sure that in the exterior of one inhomogeneity there is a corner of the other one. So these results are obtained in many papers for various configurations. So let me, before I go to the smooth inhomogeneity that is the main result of this talk, let me explain what are the techniques roughly for corner singularities. So there are typically two groups of techniques, and one is based on constructing CGO solutions, rapidly decaying solutions for the Helmholtz equation. So all this work employ this technique, and basically writing this identity using the equations for U and V, and taking a test function that is a solution to Helmholtz equation, one arrives at this type of identity. And the boundary condition cancels the boundary term here, and then there is a boundary term that it's not at the boundary of inhomogeneity, and that's why one uses CGO solutions to kind of asymptotically cancel this contribution. The other work is basically by Eichner, who in these two papers, they compared singularity, corner singularity at the neighborhood of the corner. And the contradiction is it's arrived by assuming that actually the V part solves the Helmholtz equation in the entire ball outside the corner also. Okay, so both these techniques make use, I mean, are very are designed for a corner singularity. So it doesn't look like it is possible actually to extend them to a smoother part of the boundary. So for a smooth boundary, this question actually has been attacked only recently, and a lot of progress has been made. The first paper for smooth boundary was in R2 due to Fogelius and Shaw. They proved that strictly convex inhomogeneity C2 alpha scatter every plane wave at any frequency except for at most finitely many frequencies or wave numbers. And another paper consider boundaries with points where there is a very high, so smooth but high curvature points, and some results on non-scattering by those inhomogeneities has been proven in this paper. So the major progress for smooth inhomogeneities was made in these two papers. So we looked with Michael on this question, and then we realized that, in fact, the right way to look at the non-scattering question for smooth inhomogeneity, or for any kind of actually inhomogeneity, is to connect it to free boundaries. And actually, none of us was is a specialist expert in free boundary problems, and we actually wrote this paper with the best result we could get, and hoping that people from free boundary values, regularity of free boundary community would actually jump in and probably improve the results. And actually this paper followed very soon our paper, and actually they have some stronger results, and I'll mention as I go on. Okay, so let me just briefly introduce what are these free boundary problems. Those problems are these free boundary methods apply to this type of questions where you have an equation, so elliptic equation, say Laplacian, equal to some source. And actually, it's a nonlinear by design because the source actually typically is some function, or most of the cases it's constant, and this is the characteristic function where the solution is different from zero. Okay, so it sort of divides the region where the solution is not zero from the region that the solution is identically zero, and the boundary is exactly where v and the gradient both become zero. Okay, so locally in some ball, and here is the free boundary. And typically in these classical free boundary problems, the solution is positive. So this free boundary divides between positive solutions and zero solution. So now for our problem, if you remember, if you bring this term, the lower order term of Helmholtz, to the right hand side, then this source becomes of this type. Okay, so it involves the incident field. In fact, the free boundary requires that the solution, the functions are real valued. Therefore, in order to bring our non-scattering problem to such configuration, one takes the real part of the equation for the scattered field, and then one can realize that the source term looks like this one here. Okay. And so it's a natural way actually to study the non-scattering problem using this free boundary methods. So let me tell you exactly what we proved, and then I'll show some very broad ideas how we did prove this result. So what we prove is the following: if you have a Lipschitz boundary, and refractive index in general, it's a L infinity function, okay? And so we say that the incident field V is scattered if there is no solution to this problem. So this is the problem. All functions are real. This is a real part of the incident field, okay? And this equation, we simply zoom near a boundary point, so it's a local problem. So this equation is required to be satisfied in a D intersected by a ball centered at some point Z. The Cauchy data of W are both zero on the boundary here in this ball, okay, that divides between D and the exterior of D. And at the point Z, the right-hand side doesn't become zero, is the degenerate condition. So there is no solution to this problem. Then this is basically what it means for the incident field to scattered by the inhomogeneity. So we proved that there is no solution to this problem. In other words, V is scattered, okay, by the inhomogeneity. If N and V are real analytic around this point Z, but the boundary is not analytic locally. So locally near Z, this part of the boundary is not analytic. Or N and V are both in this space, Hölder space, have this regularity, but boundary near this point Z locally is not one order Hölder higher order of Hölder continuity regular. Okay, so basically we are saying that unless the boundary is regular enough, and this is depending also on the regularity of the coefficient, then there is always the incident field always scattered, provided that the incident field is not zero at that point, right? Because this non-degenerate condition is important for the free boundary methods. So I write this here. I mentioned that N and V has to have some certain regularity, but if V it's an incident field, then actually this is always satisfied because the incident field by construction exists. So we require that the incident field solves the Helmholtz equation outside D, and therefore it's analytic. But I phrase these results in this way because, in fact, these results do not really require that V to be a solution to the Helmholtz equation in a larger domain. Basically, they just require that the incident field that appears here on the right-hand side, okay, should have a certain regularity. That's all. And if it's incident field, of course, it is satisfied. So this basically means that our scattering or non-scattering result can be interpreted as a regularity of the transmission eigenfunction, the part V of the transmission eigenfunction up to the boundary. Okay, because so if you look at this equation that I write here, basically I phrase this equation, this problem as the problem, it's a source problem in this region D locally here, and the Cauchy data are zero on this part of the boundary. Okay, so now you can have this configuration for the transmission eigenvalue problem, right? And then basically says for a transmission eigenvalue problem to have non-zero solution. So for K to be a transmission eigenvalue, V, then you get a regularity results for V. So basically you can say that if this configuration happens and N is has this, say, order of regularity, CMU around Z, and N of Z is not equal to 1, and the boundary is not Cm plus 1, then you can conclude that V cannot be Cm mu regular, right? Because otherwise you would not have solution to this problem. This is basically what our theorem proves, which is equivalent to showing that any incident field that doesn't vanish at that point scatter. So a restriction to this result is that the incident field has to satisfy this condition. So the incident field must not vanish at the boundary point Z. Okay, and this is restrictive because so if you try to use now this result to do what is done for corner singularities to prove the uniqueness with one incident wave, that this restriction presents actually difficulties. So you cannot really use this to prove a strong result, uniqueness result with one incident wave. So basically, how do we prove it? We appeal to two type of work, okay? So the first one is the higher regularity, which is based on Kinderlechner-Nirenberg celebrated paper in 1977. And that refers to much more general PDE, okay, elliptic PDE, even nonlinear. I have stated here for a linear PDE that it's closer to our application. So if you have a PDE of this form, satisfied in this region, so it's a local, so in D intersect with the ball, I'm moving the point Z to the origin just for simplicity, and the Cauchy data on the boundary here are zero. Then the result by Kinderlechner and Nirenberg says that if you start with C1 boundary and C2 solution to this problem, then then if there is such a solution, then locally the boundary has to be C1 alpha, so you increase the order. If the coefficient are CMU, Hölder continues, then the boundary is one order higher, Hölder continuity. And if the coefficient are real analytic, then the boundary has to be real analytic for this problem to have a solution. Okay, so remember, such a problem have a solution corresponds exactly to having a non-scattering configuration. So the point is that if you start with less regular boundary than C1, and less regular solution, how can you actually bring sort of first obtain this intermediate, the starting regularity for Kinder-Lechner-Nirenberg, and then get this higher order regularity that you get it for free exactly from this paper. So in order to get this starting regularity for Kinder-Lechner-Nirenberg, one uses the work by Caffarelli, and there is a lot of work on the free boundary methods. And this, we used actually this particular work by Caffarelli, but there are actually a more improved sort of papers that probably can provide results under more optimal assumptions. But what we actually did, we exactly used this work by Caffarelli, which refers to this type of a problem. So you have a source, a Poisson problem equation in this D intersect with the ball. Again, I move Z to the origin, doesn't matter. And the Cauchy data on this part of the boundary are 0. And Caffarelli's result says that if you start with Lipschitz boundary, and provided that the solution of this problem is C11, and the source can be extended in the entire ball here as Lipschitz with this positivity condition that is typically required in this free boundary. Then basically, if you start with this regularity, then the boundary has to be C1 and the solution has to be C2, which brings to the condition to apply Kinder-Lechner and Nirenberg. So it looks like we probably get for free this first step of regularity, but it's not actually that trivial because for our scattering problem, it's a lot of work actually to prove this positivity condition. So remember that our source looks like this, okay? And W is a scattered field. So one has actually to prove this positivity condition. But first we prove using potential theory that actually the scattered field for this particular, although there is a jump in the source, okay, the scattered field is C11. And this comes from the, we make essential use of the fact that W is 0 in the outside D. So if W is not 0 outside D and the source on the right-hand side has a jump across the boundary, you don't get necessarily that the solution is C11. Okay, basically our approach, we prove that the symmetric jumps from outside and inside of the second derivatives of W are bounded, okay? And using the fact that that the field is identically 0, you get that the second derivative are bounded up to the boundary, so you get C11 regularity. And then using the non-degeneracy condition, which is essential, we are able to prove that that in fact the solution W is locally positive, and therefore we can apply Caffarelli's result. Okay, and combined with higher regularity result, give us the theorem that I showed you, give us our result. This approach actually pretty much followed the work by Williams, and I'll mention at the end actually that there are some nice connections of non-scattering with other famous problems in mathematics, and this is what actually Williams was studying in this paper, and we realized that we could use that approach to attack our non-scattering question. Now, in fact, there is some more recent work than the result of Caffarelli that we used, and is this paper by Anderson, Lindgren, and Shangolian. Based on this paper, Salo and Shangolian actually were able to come up with these non-scattering regularity results, starting from more optimal starting regularity on the boundary. And I refer the audience to this paper. It's an archive and coming up soon. Okay, so now basically what we are saying here is assuming that the refractive index is analytic, then unless the boundary is analytic, then there is no non-scattering configuration with respect to an incident field that satisfies non-vanishing condition. So this is basically, our results could also be interpreted as negative results, right? So we give conditions for which there is non-scattering, there is no non-scattering configuration. How about on the positive side? I just explained that if you have a ball, then there are a lot of non-scattering configurations, right? And if it's not analytic and the coefficients are analytic, then there is no non-scattering configuration. So the paper by Salo Shangolian were able actually to provide a very nice answer, so to the positive results for analytic boundaries. Okay, so basically they prove the following: if the boundary is analytic, okay, and you pick an incident field that it's positive on the boundary, and if you prescribe the refractive index in a neighborhood of the boundary as an analytic function, then you can extend it inside as a C infinity function in such a way that D and N render this incident field non-scattering. Okay, so basically N is constructed based on the incident field that you pick up. Okay, so now the question is, are there incident fields that are positive on the boundary? And this paper also gives the answer, yes, provided that k square is not a Dirichlet eigenvalue. So this is not that, I mean, probably a big restriction in the context that for this to happen, k has to be a transmission eigenvalue. So one is excluding Dirichlet eigenvalues that are also transmission eigenvalues. So this is a nice open question. Are there k's that are both Dirichlet and Neumann and transmission eigenvalues? So that's there is no such characterization of a such set. Anyway, so this is a very nice result, and in fact this result can be interpreted in terms of Herlot's functions, so can be interpreted in terms of the injectivity of the scattering, relative scattering operator. Remember that this is related to the non-scattering configuration to happen for incident fields having this particular form, which are Herlot's wave functions. Okay, so the result by Salo and Shangolian basically say the following: that if you pick a Herlot's function that it's positive on the boundary, then you can construct an inhomogeneity that doesn't scatter this Herlot's function. Okay, so in that sense, is some answer to the question whether the far field or relative scattering operator is not injective for analytic boundaries. And basically, how do they do it? They had this result for incident fields that they are positive on the boundary, and basically by showing that Herlot's function are dense in the set of solutions to Helmholtz equation in this with respect to this classical norm. They prove it for age S, S arbitrarily large. So basically they show that as long as k squared is not a Dirichlet eigenvalue, then you can have a lot of Helmholtz functions that are not positive on the boundary. This was really a very, very nice result. Well, with Michael, we also proved sort of, I would call it like complementary result. So the question actually whether the Helmholtz functions for which in inhomogeneities at what regularity those Helmholtz functions do not scatter come down to whether there are Helmholtz functions that do not vanish at a point, right? Because that's the whole thing. So basically what we proved is the following. If there exists an infinite sequence of wave numbers associated with non-scattering Helmholtz wave functions with density in this bounded set, okay, that is uniformly bounded from below, then the non-analytic points of the boundary are nowhere dense. Okay, so this is like sort of complementary to what Salosh-Angolian prove for analytic boundaries. Okay, so these are basically the results that we prove for smooth domains. So I would like to connect all these developments to some very interesting problems, so much older problems in mathematics. So one is when I was reading the paper by Kinderlechner and Nuremberg, I noticed that it was dedicated to Hans Levy. And that reminded me actually that was Hans Levy the first in 1959 who actually posed a question along the lines of what I was describing. So basically, in R2, if you have these two elliptic equations that they share part of the boundary being the real axis, then he posed a question, can you have such two solutions that share the Cauchy data on this part, non-analytic Cauchy data, because analytic Cauchy data, you can get the results from Cauchy-Kovalevskaya. And then he proved that it's not the case. Okay, so it's in the same spirit of what I was doing for this physical non-scattering problem. And another interesting question is that actually non-scattering configuration it resembles the famous Schiffers conjecture or Schiffers problem. So remember, the non-scattering configuration is this one. Okay, so can you find V such in that solves Helmholtz equation everywhere for which this occurs with non-zero, for which this problem has a solution, right? Because V is non-zero, so it has a solution. And exactly the Schiffers problem says the same. So basically, does this problem has a solution for any lambda here? Okay, so the source in our case is of this form, more technical, more complicated, but here is one. Okay, and or this Schiffers property can also be formulated. Are there Neumann eigenvalues for which the eigenfunction has a constant trace, for example, right? So and there is a really big connection. So it resembles in the same spirit sort of type questions with non-scattering frequency. And in fact, Williams in his paper, whose approach we follow to prove our results, he was basically considering another big problem, Pompeo's property, which is integral geometry problem. But for domains that fails Pompeo's property, it is proven that they fails the Schiffers property, and then basically this problem here has a non-zero solution. And this is what he was doing. He was studying this problem in order to answer, to give an answer to Pompeo's conjecture. So So these are big problems, and interestingly enough, a new problem coming from scattering theory sort of has the same sensibility as these problems known already in mathematics. And so I finish here. Thank you for listening.
Thank you very much, Fioralba, for the very nice talk. Thank you very much. Are there any questions or comments, please? Please feel free to unmute yourself. Any questions or comments, please? Are there any questions or comments, please?
I have a non-essential comment that in physics, when you talk about units of refraction, you have n squared in the equation.
Right.
N. This can be confusing to people in other communities.
Right, you are right. I always forget about it. Actually, I wrote it here. Right, so the square root of n is C0.
Right, and also it seems that n is supposed to be not equal to 1 pointwise, right?
Okay, yes. But you see that it is defined, right? So locally, so the results are for n not to be 1 at locally, right? At the point, where is it? So at this point, but n it's, oh no, actually now here, it's regular, right? So locally n it's assumed regular, so the point-wise evaluation is, it makes sense, right? But the results that actually people have proven for non-transmission, for transmission eigenvalues, again assume regularity of n, not L infinity in D. So you define n pointwise. So n minus 1 is different from 0 pointwise on the boundary.
Okay, so what if it vanishes on the boundary? In other words, your scatterer always supposed to have some jump at the boundary, right?
So if n minus 1 vanishes on the boundary, you can generalize these results. And in fact, I didn't mention these new developments. I think Ginny is in the audience. You can actually consider n minus 1 vanishing on a portion of the boundary and obtain some results, but you have to start with higher starting regularity. I don't know whether Ginny is going to talk in 2 weeks on that, but yes, so you can have n minus 1 vanishing on portion of the boundary, and you can get some regularity result for free boundaries in that case also.
Okay, thank you.
But I didn't want to mention because that's not my work, and I think Ginny is looking at that. I took the liberty, is Ginny there, to actually advertise that.
Thank you.
Thank you very much. Are there any other questions or comments, please?
Fiora, maybe you could comment some about what part of this still holds true for anisotropic media. In other words, when you have
for jumps, actually, it's not so much anisotropic. So it is a big, okay. So if, I regret, I'm so sorry that the second slide somehow was deleted when I compiled it. Okay, so if you have here an operator that has like conductivity, even if it's not anisotropic, it's like a divergence A grad U. So if A has a jump, meaning that it's different from 1 up to the boundary, then this regularity, free boundary regularity methods do not apply straightforward. So we are looking at that question. It seems to actually presenting a more essential, essential difficulties than simply technical difficulties to make those free boundary work for that case. Now, if A doesn't have a jump, so A becomes 1 at the boundary, in that case, everything I said here could be rewritten for that case also. So forget about anisotropic. Even if it's isotropic, but has a jump at the boundary, it's still open. So we are looking at that question, but seem to be difficult.
Thank you very much. Are there any other questions or comments, please?
I would say one more thing along the lines of David's comment. For the corners, we actually consider that particular case, a more general case, sorry, of jumps in the coefficient in the main operator in this paper, but the method is along the lines of corner singularity type techniques. But that problem actually is richer. It presents sort of some challenging questions.
Thank you very much. Are there any other questions or comments, please? Okay, if not, thank you very much, Fioralba, once again, it was a very nice talk. Thank you very much, everyone, for joining. Thank you very much.